Okay, I think we can get started. So, welcome everyone to the Get Sea Level Rise seminar. We're very glad to have Dr. Paul Bierman with us today. He has been a geologist and professor at the University of Vermont since 1993, and he earned his master's and PhD in geology from the University of Washington and his bachelor's in geology and environmental studies from Williams College. His research and teaching expertise focus on the interaction of people, climate, and Earth's dynamic surface. Public science communication, including books, essays, images, and talks, is his passion. Professor Bierman has studied erosion in Australia, South America, and several countries in Africa and the Middle East. And in Greenland, Bierman and his graduate students are tracing the history of the Greenland ice sheet over the last several million years. In Vermont, New Hampshire, and New York, Bierman and his students created the first record of storminess and erosion that extended back over the last 10,000 years. Professor Bierman teaches summer science programs for highly motivated high school students and has been co-author since 2005 of an introductory environmental geology textbook and is the lead author of NSF-funded textbook Key Concepts in Geomorphology. His first publication for the general public, When the Ice is Gone, was published very recently in 2024 with W.W. Norton, and he'll be talking about that today. And his topic is New Science and Old History from Beneath Greenland's Ice, the Power of Sampling the Bed of an Ice Sheet to Understand Past Sea Level Contribution. So welcome, Paul.
Thank you so much for the introduction, and it's good to see some faces I know in the Zoom matrix there. So today I want to talk about two things. I want to talk about the science that we have been doing with about 40 international collaborators, at least one of which who was on this call, and history that I've been doing to try to place some of this science in context. And I apologize if my voice goes out. I'm on day 9 of COVID. I'm much better, but it'd be the first time I've talked for half an hour or 40 minutes. So anyway, warning if I reach for my water in the middle of this. So I want to start by basically giving you the conclusions, which at this point, there are 2 places from underneath the Greenland ice sheet where our group has identified macrofossils or subfossil material from underneath the ice. This photograph here is from Camp Century. This is Drew Christ's photograph. And the next photograph, if I can click on the right place, will show you where Camp Century is. And hopefully you can see my cursor as I move it on here. Camp Century is up in the northwest corner of the ice sheet, actually rather close to the ice margin, about 100 miles. And then we've also been working on material from GISP too. And a shout out to Dorothy Petit, who I saw was on here, who's been working very closely with a master's student who's at the University of Vermont to help identify this fossil material or subfossil material. So I want to go back in time a little bit, and I'm going to go back and forth between the historical perspective and the data that we're gathering here. And I want to go back to 1930, 1931. And I'm sure many of you know Alfred Wegener for his ideas on plate tectonics and continental drift, but actually he was a meteorologist who had several expeditions to Greenland. The last expedition killed him. That was 1930-31, but he had established the first camp at the center of the ice here, and then an eastern camp and a western camp on either side of the ice sheet. And 3 men survived over the winter of 1930-1931 living under the ice. And there's actually film from this expedition that hopefully you can see on your monitors too. And the amazing thing about this expedition was actually twofold. One, that they managed to live at the summit of the Greenland ice sheet over winter. But the other one was the introduction by Wegener and his men and engineers of mechanized transport across the ice. And you'll see them having to deal with the ice marginal zone, which was quite troublesome for getting materials up onto the inland ice itself. So they're, packing them. But this was the thing that gave them the most trouble getting up onto the ice. These were these motorized aero sleds that had huge propellers at the back. And so you can see they used draft animals, they used winches, they used people, they could use whatever they could to get these mechanized devices up very steep ice margins and onto the ice sheet. And this will finish with the aero sled actually up top. Now, this was a tough time here, but once they get it up, moving across the ice sheet. And that's a revolution because it means they can cover large amounts of territory in much shorter amounts of time. But remember, this is 1931, and we'll skip ahead to the US military, which really finished the mechanization of ice sheet research and travel. But first, let's have a look at what these folks did while they were on the center of the ice sheet, because it's directly tied to our ice coring today and our understanding of ice stratigraphy. They built a camp. The camp was built out of snow and into the snow, and you can see the surface view of the camp with their meteorologic station, but you can also see the under part of the camp where they slept and they had storage, and then this set of stairs, which turns out to be critical. The three men did live under the ice. One of them lost most of his toes that winter. And they lived again with lanterns and candles, but in their caves, it could be as warm as 20 degrees Fahrenheit, as opposed to the outdoors, it might have been minus 20 or minus 30, and there was no wind. So it's hard to say they had a comfortable existence, but they had a livable existence. This is that sketch of their camp, but what's fascinating is here, this was a trench that they dug going down, down, down into the snow, and they logged it. This man in particular, Sorga, was trained as a geologist, and he published this paper that I've cited up top there, but he spent hours and hours measuring the density of snow by cutting these snow blocks, and created this graphic in his paper in 1932, which showed that as he got 15 meters below the surface, the snow density increased dramatically. And that's the autocompaction and the fernification of the snow. But even more important than that, he could pick out individual winter and summer layers going down by their density. And so he was the first one to establish that snow and ice actually preserved a stratigraphy in the way that geologists think about layering stratigraphy. And that's critical to everything we do with ice cores today. The US military also got quite interested in the Greenland ice sheet, not initially for the science, but because they needed to get airplanes during World War II from where they were manufactured into the US to Great Britain and then onward to the European theater. And airplanes at the time, very few of them could fly the 2,000 miles between Gander, Newfoundland, and Prestwick in Scotland. They needed to refuel, and especially the fighter planes. So they would fly them first from Presque Isle to Goose Bay, and then to one of two bases in Greenland, and then to Iceland, and then on to Prestwick. This became known as the snowball or polar route. It actually approximates a Great Circle route pretty well on there, so it was one of the more efficient ways to get planes over there in terms of distance. But in the 1940s, without radar, the planes had a bad habit of falling out of the sky and getting lost and landing on the ice sheet if they were lucky, because that was a greater chance of survival than landing in the northern Atlantic. And the other thing that was interesting about Greenland at the time is the Nazis were very interested in the weather in Greenland, because it was upstream in the westerlies from the weather they were getting in Europe. So the Nazis actually established a number of bases in East Greenland filled with meteorologists, not soldiers, which after about a year, the US Coast Guard found and captured those meteorologists. But the Americans at that point learned that working on the ice was difficult, and people were dying, and the sleds they had didn't work well. And so that motivated them to better understand travel across the ice, which meant understanding the basic physical properties of ice. And we still rely on the work they did today. First organization was something called the Snow, Ice, and Permafrost Research Establishment. And its entire mission was to understand how frozen materials behaved. And this man, a guy by the name of Henri Bader, led that institution intellectually. He was trained as a mineralogist in Europe. He understood that ice was nothing more than a mineral, and he could study it the way he had studied minerals classically, and put all of his intellectual focus into guiding this organization, which then became part of CREL in 1960. A little bit of history on Bader and what he actually did. He became an American citizen after spending the war in both South America and the Caribbean. And he really was the architect of the US science investigations in Greenland in the 1950s, many of which were focused on what they called trafficability. But he also understood that ice coring was critical to understanding past histories of our climate. And so he collected his first ice core in 1950 in Alaska on the Juneau ice field as part of JERP, which goes on as a student training and research mission today, 75 years later. But the second ice cores and third ice cores were collected in Greenland at a place called Site 2, inland from where Camp Century would be. And that's actually footage filmed by Army photographers of either the second or third ice core taken in Greenland at Site 2. They didn't get very good recovery, But they demonstrated with stable isotopes that one could see the actual annual layering in the ice core, and they studied the physical properties. The Army started getting creative with housing. And this is really important because it will lead to a place called Camp Century where they could spend 6 years drilling an ice core. In 1953, they built 2 bases that looked like this. They held 16 men. They were made of metal tubes. They were installed on the ice sheet with the idea that they would be buried over time, which is why if you look at the escape hatches here, this is right after installation. Within a year, the only way the men could get out was opening those hatches, and they would extend those over time. This is what they look like on the inside. So people were moving men and materials. The fuel drums supported diesel generators from which they got their power and melted snow for water. All of this really was under the threat of Soviet and Allied states invasions over the top. So there was this paranoia that the Reds would come across the Arctic and attack North America. And all kinds of awful things would happen if Russia should win, especially to American women, which somehow were featured in many of these sort of advertisements of the time. These camps were not secret. Their locations were secret, but they weren't secret. They showed up in men's magazines. This is one from 1956 with "We've built our military miracle in the Arctic, our secret base under the polar ice." The real purpose of these things, and there's some beautiful illustrations that come with this one, but the real purpose of these were as radar sites. They were touted as scientific research bases and meteorological observation sites, but really they had radars to look for incoming Soviet airplanes. Those were operational through most of the 1950s, but then in 1959, the Army started building a place called Camp Century. And this is the map of Camp Century. The red shows the science trenches, including the drilling trench in there. Just for scale, this main street that runs down the middle is 1,000 feet long. And the Camp Century was not by any means secret. This is a diagram published in a French magazine for young adults or teenagers of what the camp looked like. There were heated barracks inside the camp. The trenches were carved by giant snowblowers. There was metal roofing. There was a nuclear reactor in here. The Air Force delivered big things with airplanes on skis, and there were helicopters. And it survived for 6 years as a base under the ice. And there's some fantastic footage again that I'll play a little bit of here. The base was powered by a nuclear power plant for almost half of its lifetime. And that meant that there were pretty much unlimited electricity for lighting the base. This is that main street with the GIs walking up and down it and the tracked vehicles moving through it. But it also meant there was power for showers and washing your teeth, but also power for drilling. And they used an electro drill for the first 4.5 years, and they swapped over to an electromechanical drill after that. But I think what it really gave the scientists there is a place to work where they had many of the comforts of home. And that allowed them to work long days, to work long seasons, to test various pieces of equipment, and to fail repeatedly, which they did until they finally got the core. Again, the base was not at all secret. It was published in magazines like Popular Science, which of course at the time were really heavily read. And they say it was dug by these plows, and you can see the movies from the time, giant snow plows imported from Switzerland to dig trenches. And the science and the people living there got to work in these prefabbed warm bunkers. They got to eat good food. These are the chefs. This is out of a National Geographic article, roasting turkeys in the mess hall. But from our point of view, what we care about is mostly they drilled. And this is their drill rig in their drill trench. And they tried multiple holes. There are 3 holes in total, and it's the third one that worked. And again, I want to come back to Bader, and luckily there is a little bit of voice narration from him and a Voice of America propaganda radio broadcast about the power of looking back in ice. I'm just going to play a little bit of that for you because I think it tells us something about a man who in the 1950s envisioned a lot of what all of us today think about for science. And that's a long time ago. It's a decade before I was born, and I'm getting old at this point. So let's listen to Bader talking about ice coring. The video you see, what's actually film you see, was taken at Site 2 in either 1956 or 1957 as they were drilling.
The purpose of deep ice coring is to get information on conditions deep down in the glacier. And since conditions are simplest on the high ice caps, this is where we have been drilling.
So you just have to imagine yourself in 1956 with a standard hard rock drilling rig and solid rods there extracting 1,300 feet of ice core. It was an amazing effort that they did. In 1966, all the coring finished and Camp Century closed. The cores were brought off the ice in these giant wheeled trailers carried by tracked vehicles. You can see the cores stood up vertically there coming off the ice. And the ice core made its first public appearance at the Pentagon in 1966. And in the center is a fellow named Chester Langway, and this is Lyle B. Hansen, the head driller, and this is a man who I don't know. But these two, Langway and Hansen, brought pieces of the Camp Century core in a cooler to the Pentagon to thank them for their support. And they did quite a stunt that was reported in the New York Times. They took pieces of that ice and they dropped it in Dixie cups full of Coca-Cola, and they let the ice melt and have the 2,000-year-old bubbles start to go snap, crackle, pop for the military brass. And that's really the last major press the Camp Century core gets. And in 1969, of course, many of you are familiar with this paper, which is Willie Dansgaard's work. And there's Chet Langway, a bit older there. And this is Dansgaard here. And they published a paper in Science of 1,000 centuries of climate from Camp Century. And these are their data, their stable isotope data. Thousands of samples involved in this, and they could see the Holocene, and then they could see the glacial maximum. And most importantly, they could see the last interglacial, MIS 5e at the bottom, in the ice itself. So we know the ice at Camp Century goes back to MIS 5e. Their time scale was a little bit wrong here. It was based completely on flow models, but that's pretty good for 1969, what they did here. At the bottom of that ice core was 11.5 feet of frozen material. And that frozen material was a mixture of ice and soil and rock. And this again is Hansen and Langway looking at that core before it was cut up. This is probably at Krell. It's probably in the late 60s, like that. And that core was very, very lightly studied. There are only 3 published papers on it before we and our team started working on this core. And the core actually vanished in 1994. It was supposed to go to the US Ice Core Repository. The upper part of the Camp Century core went there. The bottom part of the Camp Century core did not. And they've been lots of rumors of where it might be or that it was lost. But since 1994 until about 2018, nobody knew the whereabouts, at least in the American science community, of where that core was. The Danes opened a new ice core storage facility and brought together material from many freezers in Copenhagen. And when they did, J.P. Stevenson found the boxes with this core. It had since been cut up and placed in these little cookie jars like this. And it was cut presumably before it moved from Krell to Buffalo because of the little slips of paper slipped in those jars. And a small group of us was invited to Copenhagen to look at this. That's me on an April day when it was like minus 27 C in the freezer, and I did not have enough clothes on to be where I was for any extended period of time. But we were all just so amazed, as Jörg Schaefer right here, that we were looking at this core that we all had believed was lost. I just want to give a shout out to these 3 graduate students who are working with me. That's Hallie in the center, who's been working with Dorothy and Juliana and Kat. They've pretty much finished up their work. Kat's graduated and has a paper in review, and the other 2 are working on their papers right now. They are standing above the box here that holds the samples that they did their master's thesis work on in the Copenhagen freezer. And they are way better dressed than I was that day. So in 2019, the Danes shipped us 2 test samples. This is one of those. This is what they look like. Frozen, very well preserved for being out of the ice now for over 50 years. And we started to take them apart. We had, by that point, a group of about a dozen of us who were working on this, and every person in the group needed a different amount of material, a different type of material, a different grain size of material. So we started by melting the sample and extracting the pore water out of it. And then we took that melted material and we sieved it to grain size. And when we did, we had a lot of wash water, and we were saving absolutely every bit of this sample because we only had several hundred grams, and we had all these people who needed it for analysis. So nothing went to waste, and we were filtering all the water. And as we started to look into this bin, if you'll notice, there's some little things floating on the surface. And this is a video of literally the first sample in which we found these fossils. So I'm going to let it play. And we found them first by looking at them, but then we filtered them off like this so that we could save all the fossils. And if you look in the filter here, in the funnel, you'll see some of those small pieces of organic material that are floating, and you'll see others on there. And I've just animated this with green arrows. If your eye doesn't find these things, hopefully the green arrow will help you find them. And that was revolutionary when we found that. And so we have a paper, I can say this was my only aha moment in science in 30 years of doing this, of like, oh my gosh, there's fossils, and what in the hell are they doing in material from underneath the Greenland ice sheet? It was the thing I least expected when we were doing this. And in fact, there's the black and white picture I started with, but in color, that's our first view of the fossils. That's an iPhone pointed down a microscope. We didn't even have our microscope camera out. So that's what they look like. And that was unambiguous, even to a bunch of geologists who are not botanists staring down this, that we were seeing pieces of organic material. So the first paper, which I'm sure some of you have seen and read, basically reports a wide range of analyses, including the basic analysis of the vegetation. We had one sample from the top of the core that's here, and we had one sample from the bottom of the core, and that's it. And this was our initial stratigraphy at the time. Here's our top sample, here's our bottom sample. We called them both dimictons. Now we know better. The top is fluvially transported material for the most part, so small stream there. The bottom is almost certainly glacial till. And there's an ice-rich layer in the middle with debris that we're still arguing about what that is and how it got there. But we made comparisons, say, of the pore water major ions, and the upper material in blue here, very dilute. The lower material in red, high concentration of major ions in there, indicating a long residence time between the water and the soil here. We used SEM analysis in the lower sample. All of the pieces of rock are coated with clay coatings that are consistent with soil and petagenesis. The material up at the top, because it's been bounced around in a stream, has lost those coatings. We made a set of beryllium 10 and aluminum 26 measurements, which is what my mainstay is in my lab. And we determined from that the upper material had to have been buried no longer than 1 million years. That's the only constraint we can give on it with the aluminum beryllium. And the lower material had to be buried no more than about 3 million years. So now we know that we're looking at material that is, if it's not Pleistocene, the oldest stuff is just barely before the Pleistocene. And we know that the upper sediment could not have been buried for more than 1 million years. And that, at the time, was all we knew. And it fit well with the work that Jörg Schaefer's done at GISP2, where he suggested that there was no more than 1.1 million years of burial there. So now we had evidence that the Greenland ice sheet in the million-year time frame was likely unstable and had vanished at both of these places. After that paper was published, we got funding from the National Science Foundation to support a team that includes people from Denmark, from Belgium, from France, from the United States, over 40 investigators at this point working together. And Drew Christ, who was the postdoc on this project initially, went to Copenhagen, and in the -20 freezer under red light so that we could do luminescence dating, cut sections from the core, leaving an archive there. This is what one of those sections look like back in light. This is the lower part that we interpret as till. He brought that material back, did magnetic work, and about 17 kilograms of material came back to the United States in 28 samples. And let me just show you briefly the Danish freezer. And you'll see the boxes. And then this is Drew actually cutting the core. The film is from Kathy Kasich, who has actually finished a film that's going this fall for some film festivals, and then hopefully in the spring for distribution. Her film's about how we did the work and how we did the science on here, and then the conclusions from that. But this is all cutting in the dark. And they used both a bandsaw for the major cuts and then a wire saw for the minor cuts. So thanks to the Danes and to the Americans, this core was nearly pristine after more than half a century. So there are two people here that we really need to thank for this. One is Chet Langway. This is a picture of Chet just before he retired in Buffalo, and this is J.P. Stevenson in Denmark. Both of those men are in large part responsible for this core and the science we can do still being there. This is a photograph from Fountain 81. It was taken while the core was at Krell because it's not cut up. And you can see this is the only photograph we have so far of the original core sections like this. We've overlaid how they were cut into small pieces. And then Drew has put the modern pieces here on the right side. This is 2021. And you can see that it's very easy to reconstruct the core from the past with what we have today. It's mostly intact. There are two pieces missing for which we have no idea where they went on here. Those are in pink. And we have two that were thawed and refrozen in here. But everything else is intact. And that's amazing for how old this is. So this is our group, just so you know, all the people involved in this here. We've actually added a couple since this graphic was made. And we just had the first paper out from the entire group, or a large portion of the group, and that just came out in the cryosphere a couple of days ago. And it is the history and our sampling and the basic physical characterization of the core material. So it's sort of the bedrock paper, even though this isn't bedrock, for what the large group is doing in terms of the stratigraphy. And below is the data we have now from our group at the University of Vermont on the core. So of course we have the photographs, we have a stratigraphic log, we have grain size, we have the first measurements of in situ beryllium-10, which tell us a very boring story down below, but a really interesting story up above of potential stability and some exposure in those fluvial sediments. We know how much ice we had versus sediment. We have the stable isotopes of pore ice. That's with Eric Steig. We have the pH and conductivity. All of this, including the mobile and immobile cations and the organic geochemistry, supports the idea that the lower material at Camp Century is a dimict that was exposed at the surface and weathered, and that the upper material is a fluvial, a stream deposit that was probably stable on the order of at least a couple thousand years and perhaps 10,000 years. And the ice in the middle, I would say there's no consensus, but the group is leaning toward perhaps either basal ice left from a prior glaciation or the frozen snow fern that never fully was part of an ice sheet, but was buried by a stream meandering over it. Wait on that one. There's more to come with other analyses. We have also done some very detailed work on the materials itself. And this is work of Kat Collins, and hopefully the video will start on its own here. There we go. Master student who did graduate with us in May, and she did CT scanning of all 28 pieces that we had. So that has preserved, I would say, the memory of these pieces before we melted them. And it lets you go back and look at some of the stratigraphy in there. It lets you test hypotheses about deformation. You can see we're stepping down the core. This is in the 1060 piece right now, and we're going to step down from there into 1061 and 62 and 63. So you'll notice the stratigraphy as you watch these animations. The sediments are layered. There is some layering in the ice. And now we're down into material right here at the bottom of 1060, which we interpret as a slump or a debris flow of material that's come off this till. You can see the big clasts in here as you peel this away. We've analyzed so far this in, I would say, a qualitative to semi-quantitative way, and we're working now to do the quantitative grain size analysis from these images, which turns out to be fairly difficult because some of the artifacts in the CT scans. But to me, this is just a miracle that we can look inside these things before we cut them up. And now we're down in 62, so we're down in that till material. And you can see it's just full of large clasts in there, and they're angular for the most part, few are sub-rounded. It's also got a number of ice-filled cracks in it that show up in here that are indicative of permafrost action, having frozen this in the past. So we have this archive. These are all available online. If you would like to look at them, they're part of the data set that went with this paper, which is currently in review and as a preprint. All right, so we had another paper come out that threw dates on this. And this was a science paper last summer. And this is where we start getting interesting information about sea level. So luckily, even though these samples were not stored in the dark, the centers of these samples, of course, because they're solid, have never seen light. So as long as they were cut in red light, one could make optically stimulated luminescence measurements. And in fact, that's what we did. This is 1059, the uppermost sample in the stream deposits. You can see a little bit of stratification there in the sub-rounded sand. And we got an age of 416,000 plus or minus 38. And since then, Hawk, his master's student in Utah with Tammy Rittenhauer, has generated 3 more luminescence ages from that package of fluvial sediment, 417, 422, and 414. So now we have robust replication of an MIS-11 deglaciation of Greenland. And I say that because the last time these samples saw sunlight to be bleached had to be around 400,000 years ago. Those are the ages we're getting, and we're getting them quite consistently. So there was no way to get sunlight to the bottom of the ice without removing the ice. And these same samples are, of course, chock full of plant parts. So I would say this is extremely robust dating of when the ice was absent at Camp Century. And these are some of the interpretations that Hallie, along with Dorothy, has been making. And after the talk, Dorothy can feel free to correct me on some of these. These are Hallie's slides. Pictures of Hallie over here doing the work, and then some of the various subfossils that she's found mapped to what the plants look like today if you were walking around the tundra. And I really love this comparison. And she's done it by where she is in the core. If you're looking out on this side, so there's the purple arrows. The poppy is my favorite of all of these plants, very charismatic. Here we've dropped down a little bit to the next unit, and she's got other subfossils in here, including bits of aquatic insects. This is what it would look like today. That's the fossil piece that we have. Ben Kiesling was critical to this paper. Ben spun up a series of models with different initial conditions and assumptions and tried to come out with the idea of what is the smallest amount of ice loss you can have in Greenland and expose Camp Century. And he did it in terms of relative sea level rise. And so this is his suite of models here, all the different simulations where Camp Century becomes ice-free. And the model that results in the least amount of sea level rise to take the ice off Camp Century is 1.4 meters. But important to know that that's the absolute minimum rise, and he has models that go up over 5 meters of sea level rise. So what we learned from that is that deglaciating Camp Century is not a particularly sensitive indicator of what's going on in the rest of the ice sheet. And that's really important. So we know now that at 400,000 years ago, Greenland contributed at least 1.4 meters. But again, we have a limit. We can't say anything more than that. And it is plausible that nearly all of the ice sheet vanished at that point. But again, we don't have the data for that. So 400,000 years ago, MIS-11 is an interesting time. Of all the major interglaciations, it is the longest of the bunch. CO2 was somewhere between 280 and 290 parts per million. Global temperature was 1 to 2 degrees above pre-industrial. That's pretty close to where we are today. And the estimates are that sea level was 6, 8, 10, 13 meters higher than today. So that's a lot of water to come from somewhere. But I think the most important thing is going to turn out that this was a really long interglacial, that it differs from the interglacials that follow by being so long. And the gray bars show the length of those interglacials. And so we're obviously not the first to think about this. I mean, paper with the title MIS Duration, Key to Disappearance of Greenland Ice Sheet. So this is a side of Drew's that I absolutely agree with, that MIS-11 is an imperfect analog for the future. And the plants and the dates show that this long MIS warming was capable of taking the ice away there. And I think the link that Drew's made here to several papers, the Tierney paper, but also Peter Clark's earlier paper, is that the amount of carbon dioxide we are now putting and have put in the atmosphere, unless we can get it out of the atmosphere, is going to lead us to a long period of warmth. And so I think that's one of the more powerful analogies here. If that carbon dioxide stays in the atmosphere for thousands to tens of thousands of years, it most likely is going to either doom or dramatically shrink Greenland. And Drew's analogy here, this is a photo that I found from Thule actually, is if you leave the freezer open for a long time, your ice is going to melt. And this happens to be a doorway at a barracks in Thule after a blizzard. And the soldier involved can't get out, but they can store their cold ones right there in the snow outside their door. And of course, this is from Andrea Dutton, looking at temperature rises present, MIS 5e, MIS 11, and then potentially the Pliocene, and where CO2 was. And for all of these, CO2 is sub 300 ppm, and today we're at 423 when I checked yesterday. So essentially, what we are doing is now wondering, okay, if this is 400,000 years ago, the Dutton model says that 3/4 of Greenland's ice was gone, and that contributed between 6 and 13 meters of sea level rise. So this brings us to GISP-2. And GISP-2 is at summit in the center of the ice sheet. And so the difference here is that if GISP-2 is ice-free, it's really hard to have much of any of the Greenland ice sheet left because you've taken out the center. And that core was finished in 1993. And Mark Twickler graciously gave me a video I had never seen before. This is digitized off VHS, but about 10 minutes of what it was like inside the drill dome there. And of course, if you don't know, the drillers are covered in safety gear because they're drilling with butyl acetate as a fluid, which is apparently not the best thing to have all over your skin or to breathe. So they have respirators and raincoats, and that's the core barrow coming up here. GISP-2 made it to the bottom. It's the second core in Greenland after Camp Century that made it to the bottom, and then they switched drilling apparatus, and they drilled through what they call 40 centimeters of erratic boulders, 8 centimeters of till, and then they drilled in through rock. They called it granitic bedrock. I'll just leave it as granitic rock. Having been in enough glacial margin environments, it's probably bedrock, but it also could be a big boulder. And the depth measurements here, the 1.55 is actually the entire subglacial package. So that particular diagram is not correct. This is a figure amended out of the 2016 paper where Schaefer et al. Took what was left of the bedrock core and they measured beryllium 10 and aluminum 26. And this is the bedrock or the rock portion of the core down here, rock portion here. And then we this summer worked with the till that was in the PNAS paper. And these are the erratics above the till. And one of the issues that comes up now is, if you'll notice in the beryllium and aluminum measurements that were made by Schaefer et al., they combined the sample that's part of an erratic with the sample that's part of the material below. And that leads to some ambiguities in interpretation. It doesn't change the overall story, but it becomes then more permissive of other solutions. This is what that till looked like. And your scale here is 1 centimeter. Thank Deb Meese for finding these photographs that she took a long time ago in her archive, and then she sent them to me, which I'm really thankful for. This is the material that we analyzed for the PNAS paper. That's one view. This is a view from the other side. Sure looks like till when seen from that side with those angular clasts. Looks a lot like the bottom of Camp Century. Here again is the scale in centimeters. So the entire package from here to here is 8 centimeters. There's a rock they drilled through on one side here, more till down there. So not much material to work with. The material was thawed at some point and sent to fission track labs and then returned to the ice core repository. And so we got a little baggie of about 30 grams of unsorted material to work with. And when we sieved it, we found very similar things to what we found at Camp Century. Again, these are Hallie's with assistance and mentoring from Dorothy there of the things that she found. So this is salix, it's a willow, ground covering, much shrubby habitat, not the weeping willow we think about. And the wood here was analyzed by Barry Rock at the University of New Hampshire. Definitely willow wood from the way the vessels look under the electron microscope. These are spores of spike moss, a little thing that Hallie would always say you crush under your feet without knowing it if you're walking in the tundra. And then we did find a seed of an Arctic poppy again. And so here's the seed and here's the poppy. And so really short paper. This is a 1,400-word paper. It basically reports the beryllium and aluminum measurements and reports our fossil findings. And from consultation with Dorothy and Ola Beneke, the botanists working on this, their vision is that when the ice left central Greenland under GISP-2, it looked something like this, without the helicopter, that's for scale. Rocky, probably dry, exposed, minimal vegetation on there. So a hardy, rocky tundra ecosystem. And Dorothy can talk more to that when we're done. Okay, so from the Camp Century core, we know that Greenland's ice melted naturally at less than 300 ppm. And to me, and I think to many others, that makes it increasingly vulnerable as we continue to add CO2 to the atmosphere. So here we are at our current level today. Here's the core for which we have the age of 400,000 years here. And this is carbon dioxide on here. So we are pushing the climate beyond anything it's seen for carbon dioxide levels in at least the last 800,000 years, for which we have direct measurements out of Antarctic ice. And again, this was pulled a couple of weeks ago, but 423 ppm is where we were. And I think what's notable is that's 3.5 ppm more than we were a year ago. So carbon dioxide levels are not plateauing, they are continuing to rise in the atmosphere. So we know now from this that Greenland was more than 90% ice-free within the last 1.1 million years, and that's from the Schaefer et al. Paper. And we know that it was ice-free at CO2 levels at least 30% less than they are today. So this takes me to sort of Wally Broker and his, climate is an angry beast that we're all poking at with sticks, but I'll take climate out and I'll put Greenland in there, is the angry beast that we're poking at with sticks. And so there's a deglaciated part of Greenland that I picture from one of our field trips down there. But to finish this, I want to take us back a little bit. And this is a 2-page spread in Life magazine in 1962. And Humble Oil eventually became Enco, which I think was absorbed by Esso, which then became Exxon down the line. And it may be hard for you all to read this online, so I'll read a little bit of it to you. But this advertisement says, each day Humble supplies enough energy to melt 7 million tons of glacier with an exclamation point. So we've gone from a time when I was a year old and running around in diapers, presumably, when energy companies were telling us that it was great that they had enough, could generate enough energy to melt millions of tons of glaciers. This giant glacier has remained unmelted for centuries, yet the petroleum energy Humble supplies, if converted to heat, could melt it at a rate of 80 tons each second, exclamation point. So I think we have to put in context what these men did at Camp Century in the 1960s, collecting an ice core to look at change in climate. That was their mission, because the Army was worried about the climate changing and their mobility in the Arctic. That core gave us the last 100,000 years of record, and then it sat for decades, and now it's giving us a view to when the ice sheet had vanished. At the same time, Humble Oil is promoting their energy for melting ice. And if we look back again at the culture at that point, this is was published in 1960, and it's a view from a futurist. It was actually a comic, so it would have been in the back of your comics on a Sunday newspaper. It's a futurist view of the world based on Camp Century that included under ice living. And it starts with ice caps no longer prevent people from inhabiting the frozen wastes of the polar regions. The ice itself may become a shelter for future settlements. So again, just putting ourselves back in time, I think it helps to understand the enormity of what these men did to get this core out that has become so useful for us understanding the Greenland ice sheet's behavior and from that sea level change. So I'll finish on this. This is out of Mike Mann's book, and obviously it's sarcastic that melting ice sheets will lift all boats in this. But if I go up to the upper right-hand corner, that's the Inner Harbor in Baltimore, where I grew up during a king tide, and that's going to become more and more common as we melt the ice sheet. And the illustration below is from a Nature Climate Change paper that shows where that risk in sea level rise is likely to be in terms of the number of people affected by a 0.9 meter rise by 2100. And if you look at the dark orange, a lot of it is along the Florida coast, it's on the Louisiana coast, some of it's on the California coast, but significant numbers of people in the mid-Atlantic coasts are also going to be affected. And so at this point, from what we have learned in Greenland, we know that sometime in the last 1 million years, the entire ice sheet has vanished, entire by 90 to 95% of the ice sheet. We know at Camp Century that it vanished at 400,000 years ago and contributed at least 1.4 meters of sea level rise. From GISP-2, we now have fossils similar to those at Camp Century, but we don't have a firm age on when that ice left. And there are two reasons we don't. One is that we don't know that that till material was exposed to light, although the fact that it has seeds and spores in it is very suggestive that it was. But the other reason is that that material wasn't kept frozen and wasn't kept in the dark. So it can't be used for that kind of dating. And so there are a number of us now talking about the possibility of getting back down that hole and resampling. Because to me, if I look forward, the most important thing right now is that we have material from beneath the ice sheet at a number of locations. And that's starting with York Schaefer and Jason Briner in the Green Drill project in northern Greenland. That will tell us about retreat in the same way the Camp Century will tell us about retreat. It will tell us about the margins and the timing. But from a policy and management point of view, we really want to know when the bulk of the ice sheet has disappeared, because the adaptation from 1.1 meters, 1.5 meters of sea level rise versus 6 meters of sea level rise is hugely different. And the only way we're going to know that is to start drilling again, getting to the base of the ice sheet in areas that can have a whole lot of ice volume. And GISP 2 is one of those. So if we could nail down whether GISP 2 was ice-free 400,000 years ago at MIS 11, that's a huge step forward into the sort of sea level budget. All right, so that's it. Couple resources here if you guys want to follow up. Our Camp Century website is up at the top, and if you were to scan those, that would be another way to get to them. My website is the next one, and then our laboratory's website is the third one. And if you're more interested in this history and how it all ties together, this is the book that released at the end of August. It's really for a popular audience. I think a number of my friends who are scientists have read it and enjoyed it and thought it was informative. I would love it to be the kind of thing that a student picks up in an undergrad class and can say, oh, now I understand a little bit more about climate and ice cores. It's definitely not a difficult book to read, and the link to Norton's page is there. So at this point, I will shut up and take some questions.
Thanks a lot, Paul. Great. Do we have any questions?
Dorothy, any thoughts?
Nice job, Paul. I thought, especially in the context back a century ago, of the earliest work on Greenland. It's amazing.
Well, it's kind of amazing that the Wegner's group actually measured the thickness of the ice sheet using very crude seismic data. They set off explosions, and then they had geophones out there, and their estimate is not, I don't have it in front of me here, but it's not bad compared to what we think today in that same region.
Yeah, the footage is amazing.
Oh, the historical footage is just stunning. I mean, that the Wagner expedition filmed it, but then I think I'm just scraping the surface of the Army's footage. For those of you who are interested, a lot of it is on YouTube at low resolution, and a bunch more of it is at the National Archives and has not been scanned at high res. So we had to purchase the very high res sort of 4K version. But once you get it in 4K, the details you can see about what they were doing. So the one thing I'm desperately trying to find, and I have not yet, is film of the drilling at Camp Century, which I'm guessing exists, and I'm guessing it's buried somewhere deep in the archives, but it's not, certainly not public.
Paul, can I ask, so what is the obstacle of getting date information from the ice core GISP 2?
Well, the ice core itself has been dated, and the ice there goes back a little bit beyond 5E before you get into the basal ice, which is tectonized and disturbed. There are some basal ice measurements. I have not seen the data yet that involve the krypton isotope system. And I'd be very curious to see what those come back with in terms of the age of that basal ice material. But what we're after is not so much the ice itself, but the potential to date the material below. That tells us when the land surface was last exposed. The sort of intellectual conundrum to the ice is twofold. One, the oldest ice, of course, is at the bottom, and it's the thinnest and the most deformed. And so that makes dating difficult. We also don't have a lot of really good dating tools for, I don't know, 100 to 400,000 years in ice like that. People have tried the chlorine beryllium system. It's really messy from an assumptions point of view of how you do that. And so that's definitely an issue. The other issue is that ice moves, right? And so when you find ice, you then have to think, where did that ice originate? If I'm not on the divide now and have been on the divide forever, then could that ice have come from somewhere else? And so, you can speculate that, well, what if Camp Century actually was clear at MIS 5E, and the 5E ice that's analyzed there came from somewhere else because it flowed in? But then you can make arguments that Camp Century topographically is in a high area and the likelihood of the ice flowing in there is low. But I think that the best thing you could have is dating in the ice and dating below and understanding of both. Does that help?
Yeah, but I was still wondering about the below. So if you forget about the ice, then you showed that you have quite a bit of rock and sediment under. And so why is that not possible to get something out of that?
Right. So the measurements that Georg Schaefer and his group made at Columbia of the beryllium 10 and aluminum 26 show a depth profile. But the problem from the aluminum 26 beryllium 10 system is that the solutions to that depth profile are non-unique. So it's as though you end up at the grocery store, but we can't tell you how you walked to the grocery store, but we can know that you ended up at the grocery store. And that's the problem with measuring. We can make good measurements of both of those isotopes, but you can come up with a myriad of ways in which to get there. And so if you look at their 2016 paper, you can do it with one, according to their model, one exposure 1.1 million years ago of a couple 100,000 years. Or you can do it by exposing at every interglacial, or you can do it by exposing only at the super interglacials, and you end up with the same result. The definitive way we dated at Camp Century is optically stimulated luminescence, and that's Tammy Rittenhauer's lab. And that relies on sediment that has been exposed to light and then buried ever since. The problem with GISP-2 is it may have been exposed to light, and the fact that there are so many macrofossils in it suggests it probably was. But when the core was brought back, the photos I showed you of that core, it was still frozen, right? It's not frozen anymore. And so it's been disaggregated, it's been worked with in the lab, it's been exposed to room light, which would have destroyed the ability for it to be dated on there. If it had been kept frozen, then it would have been similar to what we did at Camp Century, where we could take a piece of that sediment, cut it in a dark room or a red lit room, take the piece out of the center that had never seen sunlight and analyze it. And that's what Tammy did with Camp Century. So it's a sample handling issue from GISP-2 that can be remedied by going back down that hole and drilling again and getting more till and surface materials. So we would, in fact, we were so disappointed. We actually thought we could do this when the bag was shipped to us. There was a disc of material in there that was not even a centimeter thick. I'm sure it's that piece that we saw in the photos there, where they had actually drilled right through a rock. We didn't know it was a rock. It was covered in sediment. And so I quickly packaged it up, sent it to Tammy, who took it in her dark room and started scraping at it with an X-Acto knife to clean off the oxide stuff. And it turned out to be rock covered in sediment. And so we couldn't do anything with that. But we were hoping that maybe this was a piece of clay that had hardened and we'd be able to do something. And we couldn't. So that, to me, if there's one pressing thing we need to do now to start answering the sea level question, is to poke a couple holes in the center of the Greenland ice sheet. And there was I think it's one of Ben's papers that just came out in the last couple of weeks that suggested the best place to go do that for sensitivity. It's sitting on my desk and I have not read it yet.
Thank you. Very, very interesting.
It's nice to see that those old cores and related sediments are still telling tales. When you think about getting an additional access point, how well preserved are other deep core sites that might allow you to reactivate them to get to bedrock?
I'm not the best person to answer that. I'm not a driller. I'm a geomorphologist and geochemist who does ice cores. But I know, for instance, that Di3, I believe, was melting at the bed. So the other thing I didn't mention is that you want a place that's frozen to the bed, or else you've lost a lot of that record by erosion. And so I know that the Danes are thinking about the two grip sites and working on those right now.
Yes.
But from a deep core point of view, I'm not sure that we have other holes to go back down right now to go do that. And
Well,
can you suggest where you'd go?
I'm just remembering my time at GISP-2 a long time ago and making the surface traverse over to the grip camp when it was still operating. So that gives you a pretty good time frame of when I was there.
Yeah.
But somebody knows the status of all the possibles.
And I
So
would say that someone is JP.
Yes, that would be a great guess.
Who was saying very bad things about how the GISP pole was cased and issues because he's just, JP. But I think it's obviously something fixable. And if the hole is mostly there, it's a whole lot easier than redrilling from scratch to get to the bed.
Right.
And we tried some other tricks on this, and sort of motivated by Richard Alley. There's a paper by Lee Corbett, who's doctoral level scientist who manages our lab facility. We tried sampling clasts in outwash streams and embedded in ice, hoping to get some of this information. And she has a paper, it's quite complicated, when we measured, I think, 86 clasts coming out of the ice. Most of them carry almost no beryllium-10 and no aluminum-26, which indicates they're derived from areas that are deeply eroded and not areas like Sentry or like GISP-2 that have a lot of nuclides, which tells you they've been frozen to the bed. That's actually no surprise, right? The sediment's coming from places that are eroding. But a handful of those clasts actually carry a lot of beryllium-10, a lot of aluminum-26, and tell us a little bit about the history, but nothing. The hypothesis we had failed. We hoped we would see a distribution of class that would tell us exposure times and burial times under the ice, and we didn't get that. So I think really that deep drilling and direct access to the bed is the way to do this.
Yeah. Also, happy 70th anniversary to the C-130. Your picture of the LC-130 in the background took me way, way back.
70th, wow.
It looks a lot different, the demo model.
Sure.
All right. Thank you. Great talk.
Thank you. Appreciate it. And if you need to find me, just feel free to drop an email. I'm University of Vermont, easy to find.
Thanks. Great talk.